what could possibly be the effect of changing the pH in the solubility of calcium fluoride, or any salt for that matter? Well, as soon as I think of the idea of pH, I probably am thinking about hydrogen ions, right? Because that's what pH is really measuring. So I'm thinking maybe hydrogen ions have some way of moving this equilibrium forwards or backwards. I could also think about hydroxide ions and having an effect. But if I'm taking just a plain look at this equation that's sitting right here in the center, I don't see hydrogen ions, I don't see hydroxide ions. Those ions are not in common with this equilibrium. So I'm going to have to take a deeper look at what's happening here. If I think about it a little bit outside the box, I could see that the ions that are forming here, the calcium ion and the fluoride ions, could have been part of an acid, or could have been a part of a base. For instance, I could see that hydrofluoric acid could use a fluoride as part of its equilibrium equation, right? Isn't that how it would ionize in water? I could also, on the other hand, put a calcium ion as part of a hydroxide, right? Calcium hydroxide. And I could see this breaking apart, something like that, right? And you're saying, well, that's all fine and good. Why are we making up some acids and some bases? Well, we are trying to really see if we could possibly predict what is the effect that changing the pH on this particular equilibrium would have. And then I'm trying to figure out if changing the pH is going to entail either adding some hydrogen ions or adding some hydroxide ions or decreasing any of those. If I'm changing the concentration of these ions, and I am not seeing how those ions are part of this equilibrium, I want to see if there is kind of a backwards way, a backdoor way in which those ions could actually have an effect. And this is what I'm trying to get to here. So I am seeing that calcium is actually possibly, right, it is actually part of a calcium hydroxide, which is a base, and the fluoride ions are part of hydrofluoric acid, which is actually an acid. Now, let's look at it a little bit further. This acid right here, remember how this is a weak acid? It's not one of the ones we memorized before. And being that it is weak, it is very important to see that this is going to have an equilibrium. It is not going to go 100% to the right. It's not going to 100% ionize. It's going to stay, quite a few of those molecules, more than half of them really, are going to stay covalently bonded, right, as hydrofluoric acid. The H and the F bonded as opposed to ionized, because we have a K value that is lower than 1. That speaks to it being a weak acid, right? Okay, let's now tell the same story with the hydroxide, or a similar story. I'm going to try to figure out whether this is strong or weak. Well, I had you memorize that all group 1 elements make a strong base when paired up with the hydroxide, but calcium is not a group 1 element, and I didn't have you memorize this one, but it turns out that calcium hydroxide is a strong base. Barium hydroxide is also a strong base. So it turns out that it ionizes 100%, and this is why I wrote just one-way arrow right here, because I know this to have a K value that is higher than 1. That I expect this to go 100% to the right, or very close to 100% to the right, to the point that I would say that calcium hydroxide is a soluble salt, so I expect it to be fully ionized if I was to see it in water, right? I don't expect it to be together. Okay, so whenever you are doing a problem like this and you encounter a weak acid or weak base for that matter, you're going to be suspicious of their conjugate. What I mean by that is that if you are looking at the fact that this is an equilibrium and this right here is our acid, our weak acid for that matter, right? So it's weak. And I have then a conjugate base right here. For instance, going forward, this acid donates a proton, right? and then makes, in doing that, in getting rid of that hydrogen, makes this fluoride, right? And then if you see this backwards, this fluoride can go ahead and reattach a hydrogen ion and become, right, go this way and become hydrogen fluoride. And the hydrogen fluoride could go ahead and detach the hydrogen ion and go ahead and become the fluoride ion. And this is going to establish an equilibrium, which has been what we've been discussing in class for the last month or so. Now, if I am looking at a conjugate base from a weak acid, that means that that conjugate base is not that bad at being a base. It is actually a weak base, but it's not the worst base of them all, meaning that it does a fair job at gaining a proton, right, and moving to the left, right, and going ahead and becoming what we call protonated again, which means that it would reattach the hydrogen ion again, reattach that proton into the fluoride, right, and become the covalently bonded hydrofluoric acid in the water, as opposed to the ionized version of hydrofluoric acid, which would be the hydrogen and the fluoride ions separate, right? So the reason for that being important here is that if we are to change, let's go back to the equilibrium that we looked at in the center of this slideshow right here. If I look at my fluoride ions right here, and let's say I was to do the following. Let's say that we're going to increase the pH. How do we propose we increase the pH? Well, I know, I guess we could just throw a bunch of acid into this solution, right? So let's say that we're going to throw a bunch of hydrochloric acid in here, right? And I am going to think about this in terms of the ions that are being produced and what is happening in this whole situation that now we have. We have calcium ions moving around all over the place. We have fluoride ions moving all over the place. And now we added a few more people to the party and we added hydrochloric acid. But of course, it's a strong acid, which means that what I'm really adding is a bunch of hydrogen ions and a bunch of chloride ions. And at this point, I'm not really concerned about the chlorides, but I am looking at this hydrogen ion right here. And if I added a bunch of them, imagine it to be like flooded with hydrogen ions. Now, the hydrogen ions could go ahead and collide with this calcium, and imagine they wouldn't even like each other because they're both positive. So that's a no-go, right? But if this hydrogen ion meets this fluoride, from what we know of this situation right here, the fact that this is a weak acid when protonated, right, with the hydrogen ion, and this right here is establishing this all of a sudden we made another equilibrium in this solution. We have the calcium fluoride dissolving into the calcium ions and the fluoride ions, but we now also could have this other equilibrium happen between the hydrogen ions and the fluoride ions. So that's an interesting thing, right? It's kind of taking some of the fluoride ions and involving them in this other equilibrium that involves the hydrogen ion that we're adding, right? It's not a common ion, but it's an ion that's going to affect it because it's going to start trapping some of these fluorides, almost like a precipitation. It has a similar effect. The fluoride ions that were produced by the calcium fluoride, whichever many there were, which weren't that many to begin with because this is not a very soluble salt, it establishes an equilibrium. Some of them are moving around, dissolved in the water, and all of a sudden they find a bunch of hydrogen ions available, and they establish this equilibrium right here that we see, right? They start protonating again, accepting that hydrogen ion, and going to the left, right? So making hydrofluoric acid. So basically this situation right here, right, is going to go ahead and make hydrogen fluoride, the attached version of this acid, the weak acid, right? Because it's establishing an equilibrium. And so in fact, these fluoride ions actually are going to diminish, are going to go down through time as they're bonding with the hydrogen ion. Almost, again, it's similar in at least in purpose to a precipitation, that it takes away some of the ions from the solution. So it lowers the concentration of the fluoride ions. That's really what's happening through that time. Now, If that happens, now we go and jump into what we know about shifts and Le Chatelier, right? If I end up uh, adding a change, right? Adding a stress. Oh my God, I couldn't think of the word. Adding a stress to this equilibrium. That the result of it is that we create these hydrogen fluoride molecules in water. And they're in fact taking away fluoride ions. What I'm really doing, the stress really that's happening here, is that we're lowering the concentration of fluoride ions. That's really what's happening by trapping it and making the protonated version of the hydrofluoric acid, right? The HF covalently bonded in the water. So I'm lowering the fluorides by doing that. Now what is the system going to do, right? It's going to resist that. How do we resist this thing? I'm going to have to make more of the ion that was taken away, right? So the equilibrium is going to shift towards the side that compensates for that stress, right? Compensates for that loss. So it's going to move to the right, right? It's going to make more of the fluoride that was taken away. And then what are the consequences of that? Well, let's see. If this equilibrium is moving generally to the right, right? I'm going, let's do a big fat arrow going to the right, right? This is the shift. There's a shift to the right. Are we increasing the solubility or decreasing the solubility? Well, I see a bunch of ions to the right, right? I actually don't see the solid on the right. I actually think that we're increasing the solubility now. What did we do with the pH in order to cause that increase in solubility? Well, we added hydrochloric acid, right? That means that we made the whole environment more and more acidic, right? Why? How does that relate to pH? That means that the pH was actually lowered. Remember how a low pH is a more acidic environment? So basically, if the stress is that we, right, the stress, the original stress, the actual stress that we put into the system was the addition of hydrochloric acid, right? So we made everything very acidic, which is the same as to say that we lowered the pH. So lowering that pH ended up causing a lowering of the fluoride ions, right? It ends up going down because of the formation of hydrofluoric acid. To resist that, we push to the right, which is increasing solubility. And the consequences are that you're going to form more ions, right? Become more and more soluble, right? So more soluble. So ultimately, a decrease in pH led to a higher solubility of this salt.